Hi, my name is Jeffrey. We are Group 6, which is formed by Sounding One, myself, Jeffrey, Kunjun Lee, and Kevin Sams. And today we are presenting repainting, which is a painting using the denoising diffusion probabilistic model by Andrea Luckmeyer and collaborators. This is the outline for today's presentation. I will start discussing the introduction, the problem statement, motivation. Later on, Eric will start discussing the method, why resampling and jumping is important, and Kevin will present the evaluation and objective analysis, and Lee will discuss the qualitative analysis, limitation, and demo. Let's just start. This paper is about image in painting. In image in painting, it's the task of given an image and a mask that removes some content. Your model needs to reconstruct the missing content in a photorealistic way and semantically consistent with the previous content that you keep. No, it's worth to note that this task for a given image and a given mask, you can generate multiple generation that are photorealistic and semantically consistent. This is why diffusion model is a suitable technique to using this kind of problem. Okay, assistant approaches usually they use an image dataset and a mask distribution, and they train on that in order to have a model that's suitable for this in-painting task. An example of this is a large mask in painting, or LLaMA, where basically they during training they generate a mask, they remove the content on the image, and they train the model to reconstruct the image. Also, latent diffusion model, also they use a similar approach. Okay, but the claim of this paper is that when you train a model that's in a mask distribution, when you evaluate the same model in a mask that is out of that distribution, usually do not perform well. For example, you can see these extreme cases that you can see here, and this model cannot perform well in this scenario because they were not trained on this kind of mask. Okay. What this paper proposed is let's just remove the dependency of mask distribution. They just train a model on image datasets. For example, now you have a diffusion model. Let's train just in image dataset, and then you can apply RePaint because the changes is just at inference time, and now you can generalize to extreme cases such these ones that you can see here. It's not to work that now because it's a diffusion model trained on image dataset. Now you can use any diffusion model that was trained on image datasets. More importantly, you don't need to train it. You just use the same model. And then just change the inference method by using repainting method, and then you can get this in-painting. You can solve in-painting on this task, even that you did not train your model for the in-painting task. Okay, just want to highlight that all the things that we will talk about in this presentation will be at inference time. Okay. I present this slide just to recall that the Q is the distribution for the forward process, meaning that even the noisy image, you produce a XT, which is the noisy image. And also remember that P is the distribution for the reverse process. They basically, even a noisy image, XT, they produce a XT -1, which is the noise image, by using a neural network. This notation will be useful later on in the methods part. Okay. Okay. The main idea of this paper is that when you have the in-painting task, if, for example, you have an image and then you have and you remove some content, then you have two areas. You have the known area, which is I will highlight here in red, which is the content that you keep, basically. And then you also have the unknown area, which is highlighted here in blue, which is the content that you want to produce. And then at inference time, what you feed to the diffusion model is a combination of the X known and the X unknown. Basically, the noise from the known area and the noise from the unknown area. And you combine those to have sorry. You combine those by using element-wise multiplication with the mask, and you get an image like that one. This is what the diffusion model will receive, basically, the combination of known and unknown area. But the other question is like, okay, from where we can get the known and unknown area, right? Okay, for the unknown noise, sorry, the known noise, we can get it from getting the input image and then pass the forward process. Basically, we just add noise to the input image, as you can see here, and then we can compute xt-1 known for this specific example. And now, after we have the known part, we are missing the unknown part. And for the unknown one, we basically we can obtain it by using the denoise process. By using our diffusion model of xt, then we can sample xt-1 of unknown part. I want to highlight that this xt is the combination of the known and the unknown part. Basically, you need a xt of the known and unknown in order to compute the xt-1 unknown. Okay, this is like the overall method, right? If you apply these changes to your diffusion model that you train on the image dataset, probably will not work, because the author found that you need more than that in order to have this working. And that's why I will leave you with Eric to explain more about the method in details, to explain what do you need to get this work. Okay, let me just stop sharing.
Okay, can you see my screen?
Yeah, we can.
Okay, thank you, Jeffrey, and I will go into more detail about the method and the intuition discussed in this paper. So basically, the intuition is with a mask like this, right? You're given a mask like this, and then you have an input image like this, a girl wearing this face mask, and you want to remove it. How can we create this diffusion process with a pre-trained diffusion model? It's basically when you, in the noising step, you add noise to our original image, and when denoising, you denoise the image regarding to this mask. So let's take just one step of the noising and denoising into detail here. So in just one step, noising the noising process and noise to xt-1, so you get a xt from q. And in denoising, you have the xt from p, and you denoise it into a xt-1 from p. So let's just reorganize a little bit. And in the noising step, right, we have this mask. So we take the known part, which is the red part here, and so we unmask the xt from q, and then we mask the unknown part, which is the blue part here, which in the xt from p, and then we combine them together. So in this way, we have a masked xt from p. And then we use that instead of the original xt from p, we use this mask xt from p, and we use that to denoise into that xt-1. And when we plug it back, we will have something like this, right? First we have the x0, and we add noise all the way to xt. Then in the denoising process, at each step, we will take the red part from from q, the noising step, and combine them into the next denoising step until we all the way reach to x0. Okay, that's pretty simple, but this approach has some problems. It somewhat works, but you introduce semantically disharmony, as I shown here. For example, when we mask out the nose of the stock, right? But with that naive approach, we will have some meaningful results, like the fur is correct, but it's not the nose, or the nose can be semantically different from the ground truth. Oh, the reason is in each step, we introduce a new area of the denoising image, the red area, and the red area have no connection with the generated part. The model have no idea what is going to be in the new red area in the next step. So that's where the disharmony comes from. Even though the diffusion model is good at harmonize the whole image, but it cannot predict the future. So that's why we introduced the concept of resampling. It's based on the assumption of diffusion model can harmonize the image in single steps, but these processes are inconsistent between each time step. So the solution is we repeat the noising and denoising step during the inference so that the model would have more information about the image they generated. I'll give more information in the next slide. So basically, in the original denoise step, we have XC and we denoise it to XT-1. Normally, we do the next step and we denoise it to T-2. And in resampling step, we said, no, we don't want to do that. We add noise again to this XT-1. So we have a new XT. Then we use that to denoise it again, so that the model, in this way, the model will have all the information it needs to create a more harmonized XT-1. Then we use that to feed into the next step of denoising. So in reality, the author actually used multiple steps with this resampling. They actually use R equals to 10, which basically they add noise and denoise for 10 times before they feed it into the next denoising step.
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
Another concept is jumping. So the reason is if we actually do this resampling at each step, it will make image blur and it fail to create complex features. For example, you see here, here's the input and we want to max out this little kid on this cart. And when j equals to 1, which basically means we do the resampling at each step, you see the feature is really smooth. There's almost non-complex features in this area. And as we increase the jumping length, you see more complex features showing up. So this is what we do. So what for jumping, we only do resampling every j time steps, starting from T-j-1. So for example, when we have j equals to 10 and we have 250 total diffusion steps, we only do the resampling at t equals to 230, 220, 210, and so on. And also we adjust the length of resampling according to that. So when j equals to 10, which basically we do the jumping at each 10 time steps, we adjust the resampling like this. So instead of just one step, for an XT, we denoise it to 10 steps, and then we add noise to 10 steps back to XT, then we denoise it again. So that's how we combine resampling and jumping. So overall, this is a visualization of resampling and jumping in real time. The y-axis is the diffusion time t, and the x-axis is the number of transitions. Basically, how many time you do an either noising or denoising step. As you can see here, the t is bouncing up and down in these areas. These are basically resampling and jumping. So you can see it's jumping back and bouncing up and down is basically the resampling. So until all the way to here when we reach the x0, which is the the generated result. And I will leave you with Kevin. He will discuss more about the metrics and experiments.
Okay, can you see my screen?
Yeah.
Yes, we can.
Okay, so I'll talk about the setup and the quantitative analysis. So the two data sets used in this testing are the CelebA-HQ data set, which is a high quality data set of celebrity faces, originally in 1024 by 1024, but it's shrunk down to 256 by 256 for their testing. And you'll see that at the top left of a table we'll be looking at later, and I'll be pointing out different parts of the table as we go along. So when I show you the full table, it won't look so confusing. So you have that data set, and then you have the ImageNet data set, which is also the second data set in the testing. And that's a data set, an image data set organized by things, and they also have faces in it. And you'll see that at the bottom half of the table that I'll be showing later. So this method relies on a pre-trained guided diffusion model. And they used for ImageNet, they had a pre-trained model to use, but for the CelebA-HQ data set, there was not a model, there's not a tested model. So they had trained their own model, and they used the same parameters as the ImageNet model. And they organized it into they tested it in 3 batches of over 4 GPUs, and trained for 250,000 iterations over 5 days. And you'll see RePaint listed at the bottom of each table. It'll be listed at the bottom of this table when you see it here. But they're compared to a few different methods. And they compare RePaint. Two of the methods, DSI and ICT, are autoregressive methods that they're comparing RePaint to. And you have AOT, Deep Fill V2, and Lama, which are two GAN-based methods using the comparison. So in the testing, they have a user study where they give the user 2 images and they ask the user to compare the images for realism. And every question is asked twice. So if they answer the same question multiple times the same way, and they're at least 75% self-consistent, then their answers get submitted to the study. So they use 100 test images in this testing, covering a variety of masks. And they have 5 users. Each user is asked each question twice, and you have 100 test images. So that's 1,000 votes over each method, data set, and mask. And you'll see the votes here in this portion of the table, and it's given as a ratio of votes with respect to RePaint. So for example, here, 2.4%, you have 2.4% that went to the competitor, and with a 1% margin of error. So you take this 2.4%, subtract it from 100. That basically means that the competitor received 2.4% of the user votes, whereas RePaint received the other 97.6% of the votes. So in that case, RePaint definitely won. And you'll see RePaint, like I said, it'll be listed as a reference at the bottom of the table. So like I said, that's going to, if you compare it here, that's going to be 11.6% went to the competitor, and the remaining votes and percentage went to RePaint. So regarding the masks, you'll see the masks listed across the top of the table. The mask types they use are the wide mask, where they mask out a large portion of the image. The narrow mask, where they take out smaller portions of the image. Super Resolve 2, where they take out parts of the images in horizontal and vertical lines, which kind of leaves it in a sort of a checkerboard or plaid kind of a result. And they have alternating lines mask, where they take out the second line of the second row of every part of the image, going down vertically. And they have the half mask, which they mask off half of the image, and the expand mask, where they leave just the center portion of the image and leave RePaint to fill in the outer portion. So again, regarding the user study, they have a reference mask here. This one would be like the alternating lines mask, where they just have that as a reference. The user won't see that, but the user will be asked to compare these 2 pictures for realism. And here the user selected this one because the image is, of course, a lot more clear. This one still has some of the artifacts left over from the alternating lines mask. And if they answer these questions, they'll get asked these questions twice. And if they answer the same question the same way multiple times, and they're at least 75% self-consistent, then their answers are submitted to the study. So we've talked about the masks that go across the top of the table. We have the votes we've already just mentioned. They're in this portion of the table. Now we have the LPIP score, which is basically a distance metric that compares the input image to the image produced by the model and does a distance score to compare it, and gives it a distance score as far as how far away the image produced by the model is away from the ground truth image. And keep in mind that the lower score is better. So now we'll look at the larger table, look at the full table, and here again we have the CelebA-HQ data set of celebrity faces. The top left, the bottom half of the table, we'll be comparing ImageNet. Across each table, you have the masks, and then you have the user votes and the LPIP score, which, like I said, keep in mind that the lower score is better. And here are the methods being compared to RePaint, which RePaint is used as a reference for the user votes. Remember that if you just take the user votes, subtract that from 100, that means the AOT competitor in this category received 11.6% of the vote, whereas RePaint received the remainder of the votes. So I'm going to show you the winners in red, and I'll show you the competitors in blue. You can see here RePaint in the narrow, super resolve, and alternating lines category, where it's a small mask where they don't remove a large portion of the image. RePaint does really well. It's the winner in those categories, and you have others in the runner-up. But regarding the half mask, where they take off half the image, the expand mask, and the wide mask, where they remove large portions of the image, RePaint doesn't do as well, but it does at least place. It's a second runner-up. Lama pretty much wins in those wider masks where a larger portion of the image is removed. And that was for the pre-trained model. And the model that they trained themselves, the ImageNet model, you can see here again for the narrow, super resolve, and alternating lines, the mask where they remove smaller portions of the image. RePaint doesn't win, but it at least places in the category. It's a second, kind of a second runner-up. But again, in the half mask, expand mask, and in the wide mask, where a large portion of the image is removed, RePaint basically doesn't even place in that category. It's not a winner or a runner-up. That's taken by the ICT and Lama models. And according to the authors, the reason why is because LPIPS punishes RePaint because RePaint has the ability to produce content that is very semantically different than the ground truth. So for example, if you have like a bowl of apples and you use the half mask where you take off half the image, and some of these other models will refill the other half of the bowl, it might be to varying degrees of graininess or blurriness, but they will refill the bowl with the other half of the image with apples. So you still have a bowl of apples, which is what you started with in the ground truth. But RePaint is capable of taking the other half and maybe refilling it with oranges and grapes, which is very different than the ground truth image. So LPIPS will punish RePaint for having that capability, for producing that content that is very semantically different than the ground truth image. However, in the user testing, again, where you have RePaint uses a reference, receiving the remaining percentage of these votes, RePaint outperforms all the other models, except for ICT in the half mask. This is the only category where RePaint received a lower percentage of the votes. So I'll give you an example for the half mask and expand mask where RePaint doesn't do as well. So you see here, we have the input images on this side, a bowl of fruit, two people standing next to each other taking a picture, and a bird and the bird's beak. You can see ICT and Lama, they kind of won those categories, produces content that's semantically believable. I'm not exactly sure what's going on here, but as far as the colors going back and forth and the content, it seems more believable, a little closer to the ground truth, at least according to the LPIP score. Whereas we have RePaint on this side producing a lizard, which is the color is very different. It's semantically different. You have this one where it fills in a person next to this original ground truth person, but they're in sort of a weird juxtaposition. And down here, you can see where it starts with a bird beak, and on the other side, RePaint fills in a polar bear. So it's like, where'd that come from? So that's one of the capabilities RePaint has, is that because it's, as Eric kind of mentioned, the model is not semantically aware of the content. So it is capable of producing content that is very semantically different than the original ground truth image, and RePaint, the LPIP score will punish RePaint for that. And one more example in the expand mask, where if you look at the content here, where we leave in just a small portion of the image and RePaint has to fill in the outside, or the other models have to fill in the outside. The content here is a little more believable with the ground truth for the ICT and Lama, but for RePaint, I believe this is a rear view mirror of a car, and it takes that and fills in the outside with something that's just not very well connected to the original ground truth image. Same thing for the piano. And here it takes that center portion and somehow puts it onto I believe that's a perfume bottle. So again, this is an example of why the LPIP score punishes RePaint for its ability to produce content that is semantically very different than the original ground truth image. And that's partly because the model is not semantically aware of the actual content. And with that,
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
leave you to Lee to discuss the qualitative analysis.
Hello there. Can you guys hear me?
Yes.
Screen fine?
Yep.
All right then. So continue from Kevin's part. I'm going to talk about the qualitative results. So in the qualitative result, we are going to compare several models, and mostly those models are GAN-based and autoregressive based. With the DSI ICT is the autoregressive based, and the Lama is the GAN based. So at first we're going to take a look on the thick mask there. So the thick mask basically have a pretty good result for our model, but the others, they kind of showing the blurry or some artifacts. However, our model generated result is very different than the ground truth. This is a very common behavior, as the previous members mentioned. And then in the thing mask, basically, we have a whole bunch of changeable kind of shapes, and then spread all over the images, kind of try to mimic the situation that we don't know the continuous area, but actually it's kind of like disconnect with each other. And then the DSI, ICT, and the Llama, they all have pretty bad results because the text that were generated, they are all kind of not in a shape of the letters. However, as we all know that the generating the text for the diffusion model is always difficult, but our model was able to manage to generate something that is actually that at least is kind of like a shape of the letter. And then I'm going to talk about another two additional model, which is the Deep Field 2 and the AOT. And those are the GAN-based model because we are focusing on the face now. So the first I'm going to talk about the alternative lines case. Alternative lines case basically just means that we're going to having the mask that is in a line shape with that's kind of across all over the images. However, all of those models are perform pretty bad, especially for the LT. The ST is kind of forming the shape, and the DSI, Deep Field 32, and Llama, they all have a decent result. The Llama will be the best compared with the others, in my opinion, except for our model. However, we can still see those kind of grid line shapes on the girl's face. But when we look at our models, then there isn't any. So this is another masking scenario, which is the SR2. Basically, it's just imagine that we're going to super resolute the images, but without actually following the pixel. So as the result, that we're going to have grid-like shapes of the masking of the guy. So in the AOT, ACT, they all have pretty bad result. They even have the checkerboard effect, which is quite notorious in the image generating area. I would say the Deep Field 2 and the Llama are two results that's going to be compatible for our models. However, I would say that the Llama is going to be better than the Deep Field because we have actually more image details right there. However, if we look at the Llamas and our RePaint model, the Llama actually is actually way more blurry than our models, and we can still kind of see the cross grid lines shapes right there. And this is the same for the Deep Field as well. And then I'm going to talk about the CelebA-HQ. In this database, we're going to take a look on the white mask first. So all of those models, except for the AOT, they are all doing the kind of okay. However, I would say that our model is better than the rest of them because we have more details in it. Because if we look at the chicks and of the guys and the girls, they all have the reflection, and then which means that it shares some more information that makes it more visually pleasing to the human. And then next is the narrow case. However, I would say that this is the only case that we don't have a very very good. We don't beat the other models in a pretty good way because if we look at the RePaint model with the others, they all have the blurries at the edges, which is affecting the quality of the generated hair. Usually, the Llama is kind of like the best before our models, but in this case, I would say it is hard to tell which one is better. And then the half case. So basically, all of the other models, except for the Llama, the previous models, except for the Llamas, they're all doing pretty bad, in my opinion. However, if you look at the Llama and compare with our models, although our models still have the blurries on the left for the guy, but on the right side, that we actually have a better result, less blurry compared with the Llama. And for the girls, we actually have more visually pleasing hair generated results. In the next case, the expanded cases, which means that we're going to lose our majority of information of the images and all the previous previous models, except for the Llama, are doing pretty bad. And even the Llama is kind of generating the visual acceptable images. We can still see that there's a lot of blurry around the person's face. But however, if we look at ours, that we don't have those blurry, and we also have a pretty good quality for generating the hairs. So some of the limitation of our models. So the first is the RePaint is going to be a pretty slow method. This is because we are using the DDPM first. This is already a model that is slower than again and autoregressive. And furthermore, we are going to have the resampling procedure during the inference, which means that we're going to come back and forwards during the every T step of the resampling, which makes the model even slower. And because of that, if we have like a real-time tasking, this is going to be quite difficult to actually perform. And then another one downside is we don't have the FID computation. This is because the slow of our models. To compute the FID, it will take forever to do that. And then the RePaint can produce the realistic image completely different than the ground truth sometimes. And this is because the model probably didn't have the good training images in dataset, and then the sample is kind of outside of the distribution of the training dataset. And the notable use is face anonymization. Is because this is when you don't want to show your true face, but you still have kind of like face the representing it or in some scenario. And now I'm going to talk about the demo. So this is the picture for our lovely group member, Eric. So on the left side, we're going to do the ImageNet demo for this one, and then the CelebA-HQ demo on the right one. And I want to mention that the pose of the joining images for the ImageNet is kind of like a very not common pose for the images for the image training set, which means that this is kind of like a outlier, and we are going to see how it performs for our models. So we're going to use the half max for this case. All right, and so here are some of the runs that we have. As we can all see that the masking side, they are generating some kind of weird stuff that is completely not related to the Johnny's original picture. And as I mentioned before, because sitting on the row for a person, the arms are on the sky is not a very common images and position, and the pose for the ImageNet training set. Then of course that we are going to have a pretty ridiculous result. And then another model that we're going to compare for the training set is the CelebA-HQ model. And first we have the Johnny's faces cover on the half, and we can see that it's kind of generating the faces. However, it doesn't match with the Johnny's left. And then another one is from the masking that is done by the experience by the group by the paper authors. So the masking mask right there doesn't have a pretty good generated result, and I believe probably this is because the mask is specifically made for that particular image that was covering the faces. Technically speaking, that we should also have a images that's kind of that's supposed to fit Johnny's images better. However, this is what we got. And then the narrow cases. Well, the narrow case is way much better than compared with the other two. This is because the loss of the information is not that much compared with the other two. And then the last one is the thick one, and this is not a very good one as well, because we also we're generating some ground truth image that is completely not relevant. And here is the end of our presentation. Thank you.